Galaxies. It's hard to overstate their whole number in the universe. Until a few years ago, astronomers thought that there were between 50 and 100 billion galaxies in the universe. This estimate was based on deep surveys made with the Hubble Space Telescope. We will talk about them later. However, calculations suggest that their number is at least 10 times as high. The reason is, most of them cannot be seen through telescopes. Welcome to the sequel of our journey to the galaxies. After exploring the surroundings of our Milky Way and learning all sorts of things about classification of galaxies, we want to go deeper into intergalactic space. Let's start with the fact that supernovae, exploding stars, either triggered by nuclear fusion or gravitational collapse, are repeatedly discovered in galaxies. We owe our knowledge of these objects more to extragalactic supernovae than to those occurring in our Milky Way, simply because they are so rare that no supernova has been sighted in our galaxy for about 400 years. In distant galaxies, on the other hand, they take place quite frequently. According to current estimates, 20 to 30 supernovae explode every second in the observable universe. A supernova marks the final act in the lifespan of a massive star. For a short time, the dying star becomes extremely bright, increasing its luminosity by a factor of millions or billions, and shining as brightly as an entire galaxy. Astrophysically, there are two categories of supernovae. Type 2, also known as core collapse supernovae, and Type 1a, or thermonuclear supernovae. Both varieties are very rare. The frequency of supernovae in our Milky Way is estimated at only 1 to 3 per 100 years. Therefore, they are searched for in nearby galaxies, using systematic and automated search programs. 37 years ago, astronomers from New Zealand discovered a bright supernova in our Milky Way's largest companion galaxy, the Large Magellanic Cloud, 160,000 light-years from Earth. It went down in history of astronomy as the closest supernova since the invention of the telescope. The supernova was of Type 2, meaning that it was the explosion of a massive giant star. About 2 hours prior to the first visible light observation of supernova 1987A, 3 observatories around the world detected a burst of neutrinos, lasting only a few seconds. These detections were linked to the same supernova event, and provided important evidence to inform the theory of how core collapse supernovae take place. The theory included the expectation that this type of supernova would form a neutron star or a black hole. 1987A was the brightest and closest supernova to Earth in 400 years, the first one visible to the naked eye, since 1604, but for more than 3 decades it was not clear what was hiding at its center. According to the latest results, there is growing evidence that this stellar explosion left behind a neutron star. This image is a combination of data from both the James Webb and the Hubble Space Telescope. The layers of gas and dust ejected by supernova 1987A are shown in orange. In August 2011, another supernova was discovered in the galaxy M101, located at around 21 million light-years from Earth. This time, it was a Type 1a supernova, discovered at the earliest stage of its development, which according to current theory is the explosion of a white dwarf star. Type 1a supernovae occur when a carbon-rich white dwarf in a close binary system pulls the matter from a companion star until a critical mass is reached, at which the pressure of electrons is no longer sufficient to keep the white dwarf stable, and therefore it starts to collapse. This leads to an uncontrolled thermonuclear fusion process and thus to a supernova. More than a decade later, in May 2023, another supernova was found in the same galaxy M101, which could now be examined more closely by the Fermi Gamma Ray telescope. This time we are dealing with a Type 2 supernova, but it comes as a surprise. The Fermi telescope found surprisingly little gamma radiation emitted by this supernova. Until now, It was assumed that about 10% of a supernova's energy goes into the acceleration of cosmic radiation, which in turn reveals itself through gamma rays. In the case of supernova 2023 IXF, however, the Fermi data have shown that only about 1% of the energy went into this process. This massive deviation has yet to be explained. In January 2014, students discovered a supernova in the galaxy M82 and by pure chance. Based on the light curve, this stellar explosion was also classified as Type 1a. Despite its distance of around 12 million light-years, this supernova shone brighter than all the other billions of stars in the M82 galaxy put together. On the day of the supernova's brightness maximum, on January 31, 2014, the Hubble Space Telescope captured this image. In addition, NASA also provided data that allowed astronomers to study the supernova's surroundings. We have already learned about M82 and the cause of its unusual activity. In fact, supernovae occur much more frequently in colliding and interacting galaxies than in undisturbed ones. These supernovae are probably also responsible for heating up the gas torn out of the galaxies to many millions of degrees through shock waves. The strongest supernovae are known as hypernovae. These are even rarer. Theoretically, for every hypernova, we could see 1,000 to 10,000 supernovae. According to the models, hypernovae occur during the collapse of stars with more than 100 solar masses, which are already very rare. They are probably involved in one of the most mysterious phenomena in the universe, gamma-ray bursts. These extreme bursts of radiation have been known since the 1960s. For a long time, it was completely unclear what they might be. Speculation ranged from colliding black holes to communication attempts by aliens. These bursts only last a very short time, from a few milliseconds to about a minute. This makes detailed monitoring of gamma-ray bursts very difficult, and despite decades of research, the physical mechanisms which trigger gamma-ray bursts have never really been clearly identified. One theory is that gamma-ray bursts are caused by the collision and merger of two neutron stars in a binary star system. To date, thousands of gamma-ray outbursts have been recorded, mainly by NASA's Compton Gamma Ray Satellite (CGRO). The individual bursts occur irregularly and are evenly distributed in all directions. This means that they originate from deep intergalactic space, presumably from distant galaxies. Their position can now be determined quite precisely thanks to refined measurement methods. The uniform distribution of the flashes is clearly visible. This diagram shows a projection in galactic coordinates, with the Milky Way plane as the horizontal line in the center. Different colors indicate the intensity of the individual bursts. Recent observations show that the initial enormous brightness of gamma-ray bursts is caused by synchrotron radiation during a hypernova. Magnetic fields follow gigantic jets, beams of matter, shooting out of the plume in the opposite direction and almost at the speed of light, as the dying star collapses into a black hole. Two competing models currently assume that these jets are dominated either by strong magnetic fields or by matter. We already know similar mechanisms, especially jets, associated with the supermassive black holes at the cores of most galaxies. The main difference to hypernovae and gamma-ray bursts is that these originate in much smaller stellar black holes of 100 to 150 solar masses, whereas supermassive black holes must be several million solar masses. As with our Milky Way, they are the cores of galaxies, and some of them show particularly strong activity. These high-energy galaxies are summarized under the terms active galaxies, active galactic nuclei, or AGN for short. They usually radiate enormous amounts of energy. This is why their central regions mostly outshine the rest of the whole galaxy. In many of them, huge jets have also been discovered that emanate from the black hole in the core and radiate into space. AGNs emit their radiation across the entire electromagnetic spectrum, from gamma rays to optical and radio waves. The theory of active galactic nuclei states that they must be caused by supermassive black holes with several billion solar masses. In other words, many times larger than the black hole at the center of the Milky Way. The black hole attracts matter from its surroundings through its gravity. But this material does not fall directly into the black hole due to the principle of conservation of angular momentum. Instead, it accumulates in a so-called accretion disk. Through friction, the matter heats up to hundreds of millions of kelvins, and the accretion disk releases energy as radiation. This is known as an active galaxy nucleus. If a magnetic field is present, which is usually the case, the stream of matter is torn in two and hurled into space in huge jets vertical to the accretion disk. Active galactic nuclei often shine much brighter than all the stars in their home galaxy. In this image of M106, optical and radio images have been overlaid. Two anomalous arms can be seen in the radio and X-ray range, shown here in blue. These are signs of high-energy jets, emerging from the galactic disk. Radio galaxies such as Hercules A are active galaxies which generate a lot of synchrotron radiation. Thus, radio galaxies can be compared to gigantic particle accelerators. If the jets are positioned perpendicular to the line of sight, they can be observed using radio telescopes. In this case, the radiation comes from two regions of emission, usually arranged symmetrically to the nucleus, known as dragons, short for double radio sources, associated with active galactic nuclei. These club-shaped structures are much larger than the visible galaxy itself. The radiation output in the radio range can exceed the visible spectral range by far. In normal galaxies, however, the radio emission is often much weaker than the visible light. The jets are always connected to the core of the galaxy. They consist of matter which is thrown out of the core region at almost the speed of light. As already mentioned, the bundling and acceleration of the jets is probably caused by spirally arranged magnetic fields. In some radio galaxies, however, the activity has other causes. Perseus A is sending out high levels of radio emission due to mergers with other galaxies. However, the strange gas strings that can be seen here are probably generated by magnetic fields as well. Another category of active galaxies is the Seyfert type, which are very luminous galaxies with a star-shaped center. Seyfert galaxies appear very clearly in the optical light spectrum. But probably the most famous representatives among the active galactic nuclei are the quasars, not least because they have been repeatedly featured in the media for over 60 years. Quasars show extreme luminosity. The brightest quasars reach 100 trillion times the luminosity of the Sun and far outshine ordinary galaxies. The first active galaxy to be discovered was a quasar, found in 1960. 3 years later, the astronomer Martin Schmidt determined through spectral analysis that the radio source 3C273 was not a nearby star, but, with a redshift of Z0.158, was in the region of distant galaxies. In other words, it was not a real star but quasi-star-like. So, the name quasar is an acronym for quasi-stellar object, as they were initially thought to be stars. However, their redshift values indicated that they must be billions of light years away. So, they had to be extremely bright objects. Optically, quasars appeared like dots of light that could not be resolved using telescopes. Later observations and special image processing methods showed that they are embedded in the cores of galaxies. The galaxy hosting a quasar cannot be identified on a conventional optical image. The brightness of the quasar usually outshines the faint light of the host galaxy. It was not until the early 1980s that CCD technology and new methods of computer image processing finally solved the puzzle. Later, long-exposure images taken with the Hubble Space Telescope, which offered far better resolution than ground-based instruments, were able to detect a surrounding host galaxy for practically all the quasars examined. Quasars are highly interesting objects from the standpoint of theoretical astrophysics. Here, again, their activity is explained by a supermassive black hole, only much larger and more active, which is approached by gaseous matter on spiral orbits. The gas forms a broad and rotating accretion disk, in which the frictional energy is converted into extreme heat and high-energy radiation. There is another group of AGN, called blazars. This name refers to Biela Lacerti, an object that was originally thought to be a variable star in our galaxy. Blazars resemble quasars, but are less luminous, and they also show variations in brightness. They are also characterized by very intense gamma rays. The fluctuations in brightness can be of the order of days, which indicates correspondingly small active regions. The activity is also attributed to gas jets, in which matter flows away from the core regions at almost the speed of light. It seems that the transition between the different types of active galactic nuclei, such as Seyfert galaxies, blazars and quasars, is fluid, and they all may represent different stages in the evolution of AGN. In the meantime, researchers must deal with yet another subspecies of active galaxies, the so-called ULIRGs. Of course, ULIRG is again an acronym for which astronomers have a soft spot anyway. It stands for ultra-bright infrared galaxies. They are characterized by extreme luminosity in the infrared, which in the far infrared is up to 1 trillion times the luminosity of the Sun or more. This intense infrared activity is often associated with galaxy collisions, and optical images show that many ULIRGs are indeed interacting or merging. One model assumes that the colliding galaxies cause gas to flow into the central region of the merging galaxies, finally igniting an ULIRG. Galaxies are not scattered across the universe in isolation, and it is not uncommon for two galaxies to approach each other on their orbits and move into each other's gravitational field. They either drift past each other, collide, or even merge. We have already seen this with M81 and M82 and even with our own Milky Way, although the galaxies it is currently merging with are much smaller dwarf galaxies. There are many cases of galaxies with very different masses interacting in the universe, including M51 and its companion NGC 5195. A direct collision of this kind can take hundreds of millions of years. Direct collisions of stars almost never occur, as the density of stars within a galaxy is very low. Direct passing of two galaxies is almost like interlacing fingers. Most stars fly past each other unharmed, or, in the worst case, they are ripped out of the galaxies in stellar streams. It is only the shape of the galaxy, the so-called morphology, that changes significantly during the collision, as the stars are deflected from their usual orbits by gravity. As with M81 and M82, this can lead to extreme processes such as starbursts or high X-ray emission of gas that has been heated to extreme temperatures by numerous supernovae. The two galaxies NGC 4038 and 4039 are barely recognizable as individual galaxies. The collision of these galaxies led to a shock wave. Starbursts occur in the peripheral areas. This can be identified by the unusually high number of luminous gas nebulae, star-forming regions. The disks of both galaxies are heavily deformed but still active. The interaction can also be seen in fine veils or tails protruding from the galaxies. They are also known as tidal dwarf galaxies, or TDGs for short. What we see here are stellar streams similar to those detected in our own galaxy, just like the Magellanic Stream. Filaments and bridges of matter consisting of gas and torn-off stars, pulled from one galaxy to another by tidal forces. They are also known as antennae. Like high tides at sea, they always occur in pairs and in opposite directions, due to the interplay of gravity and centrifugal force. This means that there are always two forces acting in opposite directions. Computer simulations can be used to predict the formation of the antennae. The collision tears billions of stars from their orbits, many of which are left behind in intergalactic space. As a result, the galaxy has lost some of its mass and thus also some of its gravitational pull. This simulation shows the interactions occurring when two galaxies of the same mass collide. Either a galaxy merger occurs, or the galaxies involved undergo extreme morphological changes. Both galaxies, called the mice, first came into contact about 150 million years ago, and in about 400 million years they will have merged into an elliptical galaxy. Ring galaxies are among the most impressive interacting galaxies. They have a bright nucleus surrounded by a luminous, and sometimes irregularly bright ring in the plane of the galaxy. A ring galaxy is formed when a small galaxy runs straight through the nucleus of a larger galaxy. In most cases, however, this partner can still be seen close to the ring galaxy. In this case, The passing galaxy is not one of the two galaxies visible here, as could be assumed. In fact, both have nothing to do with the ring galaxy, as they stand in the foreground. The actual culprit can be found much further away. However, radio astronomy has been able to prove his guilt. He has revealed himself through a stream of neutral hydrogen gas, which was ripped out of the larger galaxy during the passage and could be detected with radio telescopes. The intruder caused millions of stars to drift through the core of the larger galaxy. Due to the enormous increase in the number of stars, the gravitational force of the core grows considerably. After the smaller galaxy has passed through the core of the larger one, its gravity decreases due to the diminishing number of stars. This has a shock effect on the stars, which in turn are pulled inwards. They bounce off the core and drift outwards again, forming a ring-shaped structure around the galaxy's core. Meanwhile, the small galaxy intruder that triggered this scenario has long since moved further away. Yet not only stars, but also gas and dust masses between the stars move outwards again. Due to the sudden reversal of motion, the gas masses become very dense, and many new stars form within them, creating a starburst, and the ring glows bluish from the light of the newly formed stars. However, this stunning sight does not last for too long. After a few million years, the galaxy slowly begins to return to its original shape. This is in line with the theory that a permanent density wave emanating from the nucleus is responsible for the formation and maintenance of each galaxy's spiral structure. Hoag's object, a flat ring galaxy discovered in 1950, was initially thought to be a planetary nebula in our Milky Way. An almost perfect circle of blue hot stars surrounds the older reddish-yellow core of this ring galaxy. But the special thing about Hoag's object can be seen here. Another much more distant ring galaxy is visible through the ring. Considering that ring galaxies are very rare, this coincidence is truly remarkable. Polar ring galaxies are also ring galaxies, but with some differences. They are seen as the result of a subsequent merger of two galaxies. Unlike ring galaxies, they are not a temporary occurrence. The merging of galaxies is known as galaxy cannibalism. According to the theory, all of today's galaxies were formed around 1 billion years after the Big Bang from the merging of the compact galaxies that predominated at the time. Today, only about 1 to 2 out of 100 galaxies are in the process of merging. One galaxy approaches another, and initially orbits around the other. The orbits become closer and closer until the two galaxies finally merge. As in most cases, elliptical galaxies are the merger products of disk galaxies. As already mentioned, the Andromeda Galaxy and our Milky Way are moving towards each other. Every day, the distance between them is reduced by around 26 million kilometers. In around 4 to 7 billion years, we do not know for sure the two will be so close that they will lose their spiral shape. This will start a wild dance that will end in a gigantic merger. It is unlikely that direct star hits will occur, as the distance between the stars is far too great. But the interstellar gas and dust masses will collide, and the rate of star formation will accelerate. After 5 billion years, the two galactic systems will eventually form a huge elliptical galaxy that will hardly produce any new stars. We have already got to know some galaxy groups, such as the Maffei group, the M81 group or the Local group, to which our Milky Way belongs. Now let's look at some other galaxy clusters. Galaxies often occur in gravitationally bound pairs or groups. Accumulations of 3 to a few dozen galaxies are called galaxy groups, while single galaxies, known as field galaxies, are those whose nearest neighbors are more than 1 million light-years away. Stephan's quintet, in the constellation of Pegasus, is the first compact group of galaxies to be recognized as such. Only 4 of the 5 galaxies make part of this group. It does not include NGC 7320, which is a foreground galaxy just coincidentally in the same line of sight. The close bond between the galaxies leads to a strong deformation of the spiral arms of all the galaxies involved, as well as to violent star formation within the galaxies. Gas between these galaxies, which is around 6 million degrees hot, and was discovered by the Chandra X-ray telescope, is also attributed to this interaction and the resulting collision of gas particles. Roberts Quartet is a loose group located in the constellation of Phoenix in the southern hemisphere. This strongly interacting group, known as Seyfert's Sextet, is in the constellation of the Serpent. The sextet includes only 4 interacting galaxies. They lie within a range of around 100,000 light-years in diameter, which is about the size of our Milky Way. This shows how compact these galaxy groups are. In this case, this spiral galaxy is located far in the background. It just happens to be in a line of sight with the main group. Moreover, this section is not a galaxy, but a particularly bright stellar stream that has been ripped out of the galaxies by interaction. In addition, this remarkable Hubble image shows numerous galaxies far in the background. Of course, there is also a septet, namely Copeland's septet in the eastern part of the constellation of Leo. All these galaxy groups also make up the so-called Hickson catalog. In 1982, astronomer Paul Hickson compiled 100 particularly compact galaxy groups into an atlas. These groups bear the designation HCG, Hickson Compact Group of Galaxies. The Hickson galaxy groups consist of at least 4 members bound together by gravity. The groups are isolated in space, meaning that there are no other galaxies in the immediate surroundings, and the galaxies are essentially compact and very close together. It is therefore highly probable that gravitational interactions occur in these galaxy groups. The aim of the Hickson catalog was to examine the members of galaxy groups in terms of their redshift and to identify galaxies whose redshift are deviating. Yet one special type of galaxy group is even more compact, and the galaxies appear even closer together than in most Hickson groups. In 1957, the Armenian astronomer Romuald Shahbazian discovered a group of quite bright and compact objects, while examining images in the red spectral range. She thought the group, which had a diameter of 1 arc-minute, was an open star cluster. It was not until 15 years later, when astronomer Halton C. Arp pointed out the possible extragalactic nature of these objects, that the 5 brightest members of the cluster were investigated in more detail. The radial velocities measured indicated several billion light-years. The actual diameter of this group of galaxies, which was later named Shahbazian 1, is around 350,000 light-years. It consists of 20 galaxies, on average 80,000 light-years apart. That's pretty darn close, and it means that the galaxies themselves must be very small and compact. The size and compactness of the group becomes clear when compared with the Andromeda Galaxy. Our neighboring galaxy has a diameter of about 140,000 light-years. The radius of Shahbazian 1 is only 35,000 light-years larger. This means that the 20 galaxies in Shahbazian 1 are concentrated in a volume only slightly larger than an imaginary sphere around the center of M31. And although they are all much smaller, each of these 20 galaxies has a mass and luminosity comparable to M31. Later, around 400 more Shahbazian groups were found. Each identification or positioning was always preceded by a difficult search through countless photographic plates. One of the more striking groups is Shahbazian 16 in the constellation of Draco, whose individual members line up in a curved chain. Shahbazian galaxy groups are characterized by some features which are very similar to those of the Hickson groups. For example, they are also isolated in space, which means that there are no other galaxies in the close vicinity. They consist of at least 5 individual objects with very high luminosity, and the compactness of the groups is very high. The distances between the galaxies are only 3 to 5 times the diameter of a member galaxy. The galaxies are also very compact and sometimes have a stellar appearance. What makes the Shahbazian galaxy groups unique is the fact that at least half of the group members are red in color, meaning that they are brighter in the red spectral range than in the blue range. This is an indication that the galaxies are very old ellipticals or possibly isolated galactic nuclei, consisting exclusively of old red stars. The motion of the individual members of a galaxy group can be traced very precisely in a computer model. Such simulations show that by the end of a galaxy group's evolution, that is, after a period of 2 to 5 billion years, all galaxies have merged into a single massive object. In earlier stages of evolution, the high density of galaxies within a group leads to constant interaction, with collisions and intersections of individual galaxies. The ram pressure effect also occurs here, which can be compared to air drag in the Earth's atmosphere. While the stars move past each other almost undisturbed during the passage of two galaxies, the extended interstellar gas clouds hit each other so hard that they slow down and heat up. In the end, the interstellar matter remains behind the galaxies as a hot intergalactic medium, which is noticeable in the X-ray range. X-ray emission has been detected in about 40% of all shock-Bosnian groups. In these models, elliptical galaxies eventually form, from which all the interstellar gas is extracted. In the long term, this has far-reaching consequences, as star formation is no longer possible in these galaxies. After the hot blue stars and the spiral arms die out over billions of years, only the old and long-lived populations of red stars remain, which ultimately determine the spectral appearance of the galaxy groups. In terms of evolutionary history, shock-Bosnian groups represent a state of galaxy groups that lies roughly between Higson and the final stage of galaxy cannibalism. Rich galaxy clusters consist of hundreds of galaxies in a shared gravitational field and in a volume several million light-years across. The Virgo cluster is the closest large galaxy cluster. Our local group is slowly moving towards the Virgo cluster, attracted by the gravitational pull of about 2,000 galaxies. Together with the local group and the surrounding galaxy groups, they form the local or Virgo supercluster. The richest galaxy clusters even contain several thousand galaxies moving at different speeds in a shared gravitational field. Intergalactic interactions also take place in the rich galaxy clusters. According to the current state of research, they are the largest gravitationally bound structures in the universe. They often contain one or more dominant and extraordinarily large galaxies. These huge elliptical galaxies, sometimes coming in pairs, are often located near the center of the clusters. The most luminous are known as CD galaxies. With several trillion solar masses and diameters of millions of light-years, they are the biggest and most luminous galaxies known today and are characterized by a gigantic halo. They are also referred to as supergiant elliptical galaxies. A few CD galaxies have multiple cores, like the Andromeda Galaxy. Again, an evidence of galaxy mergers. With a diameter of about 6 million light-years, which is more than 50 times the diameter of our Milky Way, IC 1101 is one of the largest known supergiant galaxies. It dominates the rich galaxy cluster Abell 2029 in the constellation of Virgo at about 1 billion light-years. Like the galaxy groups, a rich galaxy cluster consists not only of visible galaxies, but contains just as much mass and thin gas flowing through the entire cluster, the so-called intergalactic medium. This gas is very hot, up to 10 million Kelvin, emitting X-rays. Radiation is so intense that the first X-ray satellite, in 1970, discovered several galaxy clusters as the first X-ray sources. Only about 5% of the galaxy cluster's mass is made up of stars and planets. Again, computer simulations, so-called n-body calculations, support the theories of the merging of more and more small galaxies into huge elliptical systems. But even all galaxies together, and the entire intergalactic medium only make up about 20% of the overall mass of a cluster. Analysis of cluster galaxies' proper motions shows that 80% of the cluster's mass must be in an invisible form. There is not enough mass from visible matter to ensure that the clusters are held together by gravity. Even the hot gas detected in X-rays does not provide enough mass. This means that most of the gravitationally bound mass consists of dark matter, whose physical nature is still almost unknown. Due to their gravity, rich galaxy clusters can focus and amplify the light of objects far behind them. This is known as the gravitational lensing effect. As can be shown by the spectroscopic determination of redshifts, the larger and brighter galaxies are members of the galaxy cluster, and most of the smaller galaxies are at a higher redshift, meaning at a greater distance, and their light has been deflected by the cluster in between. Light rays deflected by a gravitational lens are bent more strongly in the direction of the mass, the closer they pass it. A gravitational lens focuses the light passing the mass onto the axis between the object and the observer. However, the light rays that pass the object intersect the axis at different distances. The resulting light distribution is therefore more of a random product. This effect is made up of the lensing of all the cluster's galaxies and a large amount of dark matter. Without the presence of high quantities of dark matter, gravitational lensing and the resulting effects cannot be explained. Today, the mere fact that light is deflected by mass is considered the most important proof of the general theory of relativity. At the beginning of the 20th century, Albert Einstein predicted that light, like all electromagnetic rays, is deflected in a gravitational field. The gravitational lensing effect has also proved to be an extremely profitable fact for astronomical research. Masses that act like gravitational lenses are now standard instruments in astronomy. They help astronomers to determine the masses of cosmic objects, as well as the structure and expansion of the universe. Some of the images are created when 2 or 3 multiple images from the same source come so close together that they become one. At the same time, the arcs become much brighter. One benefit of these observations is that they can be used to closely examine the mass distribution in the center of rich galaxy clusters. It can be used to determine how much of the overall mass must be present in the form of dark matter and whether the heaviest galaxies are also located where most of the dark matter is present. Unfortunately, the mass of galaxy clusters is often only sufficient in their central regions, so that gravitational lensing effects only occur here, and not throughout the entire extent of a cluster. This is why only a limited number of galaxy clusters can be investigated, and only around their respective centers. However, gravitational lensing effects can also be observed in smaller objects. Here, the light of a distant quasar is split into 4 images of different brightness by the lens effect from a foreground galaxy. The lensing galaxy is in the middle, forming a cross with 4 lensed images. The mass in the ring surrounding these 4 quasar images must be equivalent to 20 billion suns to explain the observed image splitting. Without the lensing foreground galaxy, this quasar would only be visible once, approximately in the middle of the 4 images, and it would appear much fainter. Sometimes these effects look ring-shaped, which is referred to as an Idstein ring. As with ordinary gravitational lenses, we can see the distant object several times. If the object is located exactly behind the lensing galaxy, the images appear as ring segments around the galaxy, and under ideal conditions, even a complete ring can be seen. Only a few Idstein rings can be viewed from Earth, as the source of the radiation must be located exactly behind the gravitational lens. In addition, these objects are very small. The apparent diameter of Idstein rings is only a few fractions of an arc-second. In NASA's CLASH program, which stands for Cluster Lensing and Supernova Survey with Hubble, astronomers made use of the gravitational lensing effect. As the name suggests, this project also identified distant supernovae which are magnified by gravitational lensing. Once again, these objects would not be visible at all without the effect of gravitational lensing. Imaging them required not only the lensing effects of the galaxy clusters, but also the combined power of both the Hubble and Spitzer space telescopes. In 2012, this led to the discovery of a galaxy which probably formed around 420 million years after the Big Bang, when the universe had reached just 3% of its current age. The light from this object traveled 13.3 billion years until it reached us. One of the goals of the Hubble Space Telescope mission was to obtain high-resolution images of distant galaxies that could not be made from the ground. Above the atmosphere, Hubble was free of atmospheric interference, making it much more suitable for ultraviolet observations than telescopes on Earth. Therefore, just a few years after its launch, it was used to take the first of several deep images with the maximum resolution technically possible at the time, in December 1995. The spectacular result was known as the Hubble Deep Field, or HDF for short. This photo became a milestone in astronomy and the source of more than 400 scientific publications. For the HDF, a small spot in the constellation of Ursa Major, the Great Bear, was selected, far from the galactic plane and without brighter foreground stars in its vicinity. This area measures 144 arcseconds across. It is so small that only a few stars of the Milky Way are in it. In comparison, this is the apparent size of the full moon in the sky, which has an angular diameter of about 900 arcseconds or 30 arc-minutes. The images were taken over a period of 10 days. Exposure times for the individual wavelengths were up to almost 43 hours. The HDF shows roughly 3,000 galaxies. Among them are the youngest after the Big Bang, and thus the most distant observed so far. The Hubble Deep Field also showed a much higher proportion of deformed and irregular galaxies than in the local universe. This suggests that galaxy collisions and mergers were much more frequent in the young universe than today. After this success, the scientists of course felt like doing more. As new and improved instruments were added to the Hubble Space Telescope, its performance and the image resolution increased. The follow-up project was the Hubble UDF, or Ultra Deep Field. From September 2003 to January 2004, 2 deep images were taken, each from the northern and southern hemisphere. Both were made from more than 800 single exposures taken by Hubble during 400 orbits around the Earth. The total exposure time was 10 and 11 days. The 2 ultra-deep field images each show around 10,000 galaxies. Again, these were the faintest galaxies observed to date, and therefore also the most distant. The light propagation time from the most distant galaxies to us is therefore more than 13 billion years. According to the standard cosmological model, the Hubble UDF looks back to the early days of the universe, around 800 million years after the Big Bang. The image thus shows some of the first galaxies that formed after the so-called Dark Ages. Research into the formation and development of galaxies was the main motivation for the Hubble UDF project. This galaxy appears abnormally red, even in an infrared false color display. It has been found to be the oldest galaxy in the ultra-deep field. In 2010, its redshift was estimated at C8.55, which means that the light has been traveling towards us for 13 billion years. However, due to the expansion of the universe, this object is now 30.3 billion light-years away from us. Again, the Hubble team went one step further in 2012. They combined images from the past 10 years to create the Hubble Extreme Deep Field, XDF for short. The result was an image with a total exposure time of 23 days. Here, too, the XDF represents only a tiny part of the sky. The selected section of the sky corresponds to about 1/10 of the diameter of the Moon as seen from Earth. Almost all light dots in this picture are galaxies. The faintest visible galaxies are 10 billion times fainter than the stars visible to the naked eye. The XDF looks back up to 13.2 billion years into the past. This means that we can see galaxies that were formed 450 to 500 million years after the Big Bang, but also many younger and closer galaxies. Due to the limited speed of light, these deep images allow objects to be imaged at different times, so the process of galaxy formation and growth can be studied. As we already know, according to the current model of galaxy formation, galaxies grow mainly by merging with other galaxies. Under the influence of gravity, dark energy, and dark matter, the first proto-galaxies, which were still quite low in mass, formed in the early universe. It is thought that these galaxy precursors gradually merged through collisions to form larger and larger galaxies. We may be seeing some of these early stages of galaxy evolution on deep images such as the XDF. In fact, most of the galaxies seen here are much smaller and less massive than the galaxies that surround us today. Most of them are barely larger than the dwarf galaxies orbiting our Milky Way, but they are many times denser, more massive and more luminous. This image shows a section of the sky of the size of the full moon, located in the southern constellation of Fornax. This section is therefore significantly larger than the Hubble UDF, in which more than 40,000 galaxies and even several hundred quasars were found. The image is made up of a total of 78 individual images taken with Hubble's ACS camera. It was created as part of the GEMS project, short for Galaxy Evolution from Morphology and Spectral Energy Distributions, which investigated how the size, shape, and structure of galaxies have changed over billions of years. One objective was to determine how the interactions between galaxies have influenced their subsequent evolution. This is a combined image of 80 bright galaxies in the GEMS field, showing a wide variety of shapes, sizes, and structures. GEMS provided an insight into the childhood and adolescence of galaxies, and the first solid evidence that galaxies grow through mergers. The distances of over 10,000 galaxies were also measured. From this, it was possible to calculate the light propagation time from each galaxy to us, and thus also its age. In another study, by NASA together with ESA and ESO, the Great Observatory's Origins Deep Survey, GOODS for short, two fields with a total size of roughly 300 square arc-seconds were examined, making them somewhat smaller than the GEMS field. The two fields are located in the proximity of the Hubble Ultra Deep Field North. The aim of this investigation was to obtain as much and as deep as possible data, long exposure times, over a broad wavelength range, from X-rays to radio. Various NASA and ESA space telescopes, Hubble, Chandra, Spitzer, XMM Newton, Herschel, as well as the largest observatories on Earth, such as ESO Very Large Telescope, Keck and Gemini, were used in both the optical and near-infrared range, and their data were combined. In this way, a three-dimensional model of a small section of the observable universe was created. This picture was the outcome, and it provided the shocking realization that there are at least 10 times more galaxies in the universe than previously thought. There must be around 3 trillion galaxies in total. However, most of them, around 90%, are so small and faint that they cannot be observed directly with today's technology. We heard earlier that the Hubble sequence was originally intended to reflect the evolution of galaxies. Until now, it was known that the sequence was valid within the last 8 billion years. Observations, carried out as part of the Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, CANDELS for short, even allowed us to look back as far as 11 billion years. At this distance, mainly low-mass galaxies had previously been studied, but not larger galaxies such as our Milky Way. The CANDELS observations have shown that galaxies of this period can also be categorized according to the familiar classification scheme. There are large differences in the percentage distribution of morphological galaxy types. In general, it can be said that irregular galaxies were much more common in the past than they are today. This is a Hubble diagram for galaxies in our immediate vicinity, the advanced stage of galaxy evolution. We are observing 72% spiral galaxies and only about 10% peculiar, meaning irregular galaxies in our local universe. Now, this is a Hubble sequence for galaxies as they existed 10 to 11 billion years ago. The tuning fork has changed into a V-shape with a cluster. The proportion of irregular galaxies was the highest at 52%. This confirms very well the evolutionary model currently prevailing in science. These smaller and low-mass irregular galaxies merged into larger ones over time, which is why the percentage share decreased. The ratio of spiral galaxies to barred spirals was also the reverse of today. About 10 billion years ago, only 20% of all spiral galaxies had a central bar. Today it is almost the opposite. About 70% of all spiral galaxies in our cosmic neighborhood are barred spirals. When Hubble's successor, the James Webb Space Telescope, was launched in 2021, it also marked the beginning of a new era of deep sky surveys. The Cosmos Webb project will go beyond the dimensions of any Hubble survey. With more than 200 hours of observation time, Cosmos Webb will use the near-infrared camera to examine a large part of the sky, 0.6 square degrees in size. This corresponds to the size of 3 full moons. At the same time, the mid-infrared instrument will map a smaller area. Since a much larger area is covered than in all previous projects, it will be possible to study large-scale structures at the beginning of galaxy formation. It is hoped that the large-scale distribution of dark matter from galaxies can be mapped back to very early times. Clusters of galaxies are by no means the largest structures in the universe. There are much larger ones. Galaxy clusters join to form superclusters, which in turn are connected by chains of smaller clusters and groups of galaxies. The local or Virgo supercluster, to which our local group also belongs, is at the center of this map. In between we can see huge empty spaces in which almost no visible matter can be observed. These empty spaces are also known as voids. These huge areas are presumably not entirely empty, at least there are no or very few galaxies within them. As a result, the universe has a huge, interconnected structure of galaxy clusters. Surveys of the sky like this one show a sort of cosmic network made up of long strings. The galaxies are particularly concentrated where several such strings meet, and these are bounded by the voids. This large-scale structure of the universe can be compared to a loose soap scum. The visible matter is arranged in long threads that look like the edges of soap bubbles. In between are the voids. The threads meet at nodes where the matter is arranged in galaxies, rich galaxy clusters and superclusters. These filaments are chains of superclusters. They form the largest and most massive known structures in the universe. One of the largest known superclusters is the Shapley supercluster SCL-124. The Milky Way is also part of a supercluster, the Laniakea supercluster. It is made up of more than 100,000 galaxies, including the Virgo supercluster, the local group, and all the galaxy groups in our neighborhood, such as the MAF-A and the M81 group. The lines represent the motion directions of the galaxies. Astronomers have analyzed a database in which the movement of more than 8,000 galaxies is recorded. Using this data, they subtracted the expansion of the universe to obtain this map of the overall motions of galaxy clusters and field galaxies. Laniakea is manifested by different strings of galaxies all moving towards a center of mass, known as the Great Attractor. This is a particularly massive region that was already known to influence our entire cosmic surroundings. However, the Great Attractor is only the fourth largest structure in the universe. For its part, it is just a supercluster, although with a mass in the order of 10 quadrillion solar masses. Together with the other galaxies of the local supercluster, the Milky Way is hurtling towards the Great Attractor at a speed of around 1.5 million kilometers per hour. The gravitational center is in the Norma cluster, south of the constellation of Scorpio, difficult to observe as it is almost completely hidden in the plane of the Milky Way as seen from Earth. Even larger is the Great Wall, which was discovered in 1989 during a systematic survey. This dense arrangement of rich galaxy clusters is around 500 million light-years long and the third largest known coherent structure in the universe. The center of the Great Wall is identical to the Coma supercluster. Second place is awarded to the Sloan Great Wall. It was discovered in 2003, based on data from the Sloan Digital Sky Survey. This structure consists of dozens of superclusters and is almost 3 times the size of the Great Wall, and has a length of around 1.4 billion light-years. The current frontrunner is a coherent cluster of 73 quasars in the constellation of Leo, which stretches over almost 4 billion light-years, known as huge LQG. LQG stands for Large Quasar Group. Such clusters of quasars have been known for some time, but this discovery in 2012 left everything in the shade. With over 3 trillion solar masses, the structure is around 18 million times more massive than the Milky Way. In the meantime, another structure has been found that is thought to be even larger. However, there is no certainty here. The Hercules Corona Borealis Great Wall is a possibly existing cosmic superstructure, which presumably consists of superclusters. If it really exists, it will have a size of 10 billion light-years. This would make it the largest and most massive known structure in the observable universe, even ahead of the huge LQG. However, it cannot be ruled out that the Hercules Corona Borealis Great Wall is made up of non-coherent structures that happen to have the same redshift. This is an example of a computer simulation of the large-scale structures of the universe. It is not visible matter that is being shown here, but dark matter. Dark matter forms the basis of visible matter. The same applies here as for the spiral structure of galaxies, the formation and cohesion of galaxy clusters, and the effect of gravitational lensing. Nothing happens without dark matter. At least that's how it looks so far, but more on that in a moment. These computer simulations only run if more than 63% dark matter is added to the amount of visible matter in the universe. In some simulations, even up to 85%. This is the only way for the computer models to simulate how the matter arranges into filaments over time, similar to the large-scale structures observed in the universe. In addition, the influence of dark energy must be included in most calculations. Dark energy makes up 68% of the mass of the universe, and we know even less about it than we do about dark matter. For almost 8 years, the Visible Multi-Object Spectrograph, VMOS for short, of ESO's Very Large Telescope has created a three-dimensional map of galaxies of the southern sky. In 2016, a total of 440 hours of observation time went into the VMOS Public Extragalactic Redshift Survey, or VIPERS. After measuring the spectra of more than 90,000 distant galaxies, a map was created that covers a 24 square degree area of the sky, extending to a distance where the universe was only about half as old as it is today. Another team of astronomers has scanned a large part of the sky at 5 different wavelengths and created a map of almost 1.2 million galaxies as part of the Sloan Digital Survey, which has been running since 1998. This data has since been used to find out how the distribution of matter has evolved over time and how the filamentary structure of the universe has come about. Cosmologists assume that tiny fluctuations in the density of matter shortly after the Big Bang are responsible for this structure of the universe. These density and temperature fluctuations have been found in the cosmic background radiation, so to speak the echo of the Big Bang, dating back to a time when the universe was almost 380,000 years old. The main problem is that cosmology is not yet in a suitable position to make clear statements about the properties of these fluctuations. According to current scientific knowledge, the beginning of the universe was very dense and hot. This state is known as the Big Bang, even if the name was originally invented to mock this theory. Today's model suggests that the Big Bang took place 13.8 billion years ago. Shortly after the Big Bang, the universe was filled with elementary particles, protons, electrons, and neutrons, which were in thermal equilibrium with radiation. The light particles, the photons, were initially constantly scattered by free electrons on their way, so that they could not propagate unhindered, like sunlight which is repeatedly scattered by water droplets and therefore cannot penetrate a rain cloud. The early universe was therefore impermeable to light. It was dark and very hot. What's more, there was no light at all and no electromagnetic radiation. More precisely, there was no difference between radiation and matter. They were coupled together. This epoch, which is said to have lasted around 380,000 years, is also known as the Dark Ages. After the Big Bang, matter continued to expand and so did space-time. Observations show that this expansion is continuing today and will accelerate in the future. The most important evidence for the Big Bang is cosmic background radiation, which was discovered in the 1960s. It is the oldest radiation measurable. When the universe cooled down to around 3000 Kelvin, some 380,000 years after the Big Bang, neutral atoms were formed in which the free electrons were bound. Now radiation and matter have decoupled. It was only then that photons were able to spread freely throughout the universe. These photons originating from the time of the decoupling of matter and radiation can still be measured today as cosmic background radiation. Due to the expansion and cooling of the universe from 3000 Kelvin to around 3 Kelvin, the original wavelength of the cosmic background radiation has stretched and is currently in the microwave range, where it was discovered in 1964. For a long time, it was assumed that this radiation was homogeneous, meaning uniform. The weak fluctuations in the temperature and density of the radiation mentioned earlier were only discovered much later. In 1989, NASA launched the Cosmic Background Explorer, COBE, a satellite specially developed for precise research into microwave background radiation. The Wilkinson Microwave Anisotropy Probe, WMAP for short, which was launched in 2001, likewise measured the background radiation until 2012, but with a resolution 30 times better than COBE. Accordingly, the density and temperature fluctuations appear in greater detail and over smaller areas. The most recent mission to research the microwave background was led by ESA and is named after the discoverer of the radiation law, Max Planck. Its results, again, show a significantly higher resolution of the temperature and density fluctuations. One of the big questions was where this radiation comes from. Matter and radiation were not perfectly uniform at the time of decoupling. It is assumed that during the sudden expansion of the universe, a phase known as inflation, tiny quantum fluctuations occurred in the density of matter and thus also in the temperature. In the somewhat cooler regions, the free electrons were captured earlier and the radiation also decoupled from the matter somewhat earlier than in the slightly hotter regions. This created tiny inhomogeneities, which can be measured today as temperature and density fluctuations in the background radiation. Since the formation of the microwave background, these originally tiny fluctuations have grown, due to gravity and the expansion of the universe into the large-scale structures visible today, especially during the inflationary phase when the universe expanded at enormous speed. Huge gas clouds condensed under the influence of dark matter and collapsed to form supermassive black holes. These are the centers of all galaxies, and they played a major role in the formation and evolution of galaxies. After their formation, the galaxies evolved by merging with other galaxies and forming galaxy clusters, which in turn arranged themselves into superclusters, filaments, and voids. Today, new galaxies are rarely formed, at most through the merging of smaller galaxies into larger ones, because there is no longer enough matter in the universe concentrated in a single place for a new galaxy to form spontaneously. New stars only emerge in galaxies where clouds of gas and dust are still present. Just as the galaxies have stopped forming, one day the stars will also stop being formed. Because one day there will no longer be any galaxies in which enough gas and dust is present to make new stars. As in the elliptical galaxies, star formation in the Milky Way will also come to a standstill, one day in the distant future. The James Webb Telescope recently discovered several galaxies that were formed only about 300 million years after the Big Bang, in other words, from about 13.5 billion years ago. This makes them the oldest and most distant galaxies ever seen. But as so many times before, each new discovery raises new questions. The most distant and therefore oldest of them, discovered in May 2024, is called JADES, GSZ 14-0. This object shows a redshift value of Z14.2. What is surprising and unexpected about it? Like the other galaxies discovered by the Webb telescope, it was significantly brighter, larger and more massive than assumed for conditions at that time. And so, researchers wonder, why are these galaxies in the early universe so large and bright? According to the current model of galaxy formation, we should only find small galaxies. Since then, the existing standard model of cosmology has increasingly been called into question. Doubts were raised in particular about the influence of dark matter. Now, competing models are being reconsidered, such as the MOND theory, which stands for Modified Newtonian Dynamics. In this theory, dark matter doesn't exist at all. According to MOND, the matter which forms a galaxy quickly assembles and initially expands with the rest of the universe. Gravity slows down and reverses the expansion, causing the mass to collapse and to form a galaxy. Meanwhile, computer simulations have been carried out that lead to the formation of galaxies without considering the influence of dark matter. However, the results of these simulations also do not match reality in all respects. Especially in cases where dark matter appears to be indispensable, alternative theories do not yet provide satisfactory answers. Neither with the explanation of the spiral structure or the rotation curves of galaxies, nor with the obvious lack of mass in present-day galaxy clusters. Nevertheless, I have no doubt that future research will answer some of our biggest questions and bring further insights into the incredibly fascinating world of galaxies. So, let's look forward to it. As always, please hit the like button, and I would appreciate it if you subscribe to support my channel. Thank you for watching and see you next time.